Welcome back, everybody, to the Cloud Native Platforms track. We've had so many good sessions so far already today, but I'm very excited to introduce this next section to you. We have Alvaro Munoz and Tony Torralba from GitHub here to talk about security as code, a DevSecOps approach. And if you paid attention to the TAP discussion today, the Tanzu application platform discussion today, you'll know that VMware believes very strongly as well that the automation of security in the DevSecOps tool chain is a really critical step. And these guys have a really interesting technology to talk to you about today and approach to talk to you about today. So without further ado, I will hand it over to Alvaro and Tony. Take it away, guys.
Hello, welcome to this session. This is Security as Code, a DevSecOps approach. And my name is Alvaro Munoz. I'm a staff security researcher with the GitHub Security Lab. And here with me today, my colleague, Tony Torralba, which is a CodeQL engineer. And we will be talking a little bit about what shifting security left implies and how to perform or implement security as code using a language that we are going to introduce you today, which is CodeQL. So first of all, let me start with something that looks like a science fiction story, but it's actually a real one. So 9 years ago, if you remember, when the Curiosity rover was landing on the surface of Mars, or it was going to land, the NASA engineers performed a code review of the code base of the software that was responsible for opening the parachute of the Curiosity rover on the surface of Mars. So at that time, they found this little bug in this little piece of C code, which basically means that, well, we have a function taking a 12-dimension array, and then we have an invocation of that function, which is invoked with an array of only 3 items. So this is possible in C, and what is going to happen is that when we are iterating through the different elements of the array, that we are going to basically pass a pointer, and we are going to move that pointer and read some position, some data in the stack. So what is going to happen is that for the 3 first items, we are going to read real coordinates for the landing. But then we are going to start reading some memory, some data that is in the stack adjacent to this space reserved for the array, but that is not part of this array. So this is going to means that we are going to read an initialized memory, or in the end, we are going to read some garbage. And that can lead to a crash, but not just a software crash. In this case, a literal crash of the Curiosity rover on Mars. So at that time, what the NASA engineers did was basically write this piece of CodeQL, that you can see in the right of the screen. And this is basically a little query that you can even, I think it's tweetable. It's like it fits in one tweet. And what it's looking for is like the discrepancy between definitions of a function and the invocation of those functions with different sizes of the arrays. So by doing that and running this query, not just in that particular piece of code where they found the bug manually, but also in the whole code base of the Curiosity rover software, they found other 30 variants of this code. And we all know how this story ended, right? So Curiosity landed safely in the surface of Mars, and that was a little bit thanks to CodeQL. So if you think about it, that was very late in the process of the development lifecycle, right? So moving that patch to production means like fixing that piece of code mid-flight while the probe was flying to Mars. And that's pretty expensive, I can tell you. So this year, you know that NASA sent another rover to Mars, in this case, Perseverance, but this time they did something very important. They saved security left and they moved security activities to the beginning of the life cycle. So they basically integrated CodeQL from the very beginning of the development of the software, and they integrated that into their build pipeline, in this case, using GitHub Actions. So before jumping into what security as code is and how it can help you prevent introducing bugs into your code, let's first review what are the main challenges of shifting security left. So as we saw in the NASA example, if we don't do that, if we keep these security activities to the right of the development lifecycle, that means that it's going to be very expensive and very few, not effective and efficient at all to fix those bugs. So before jumping into that, let me first address what I think that are the main misconceptions of what shifting security left is. So I think that the first misconception is that a lot of people that I talk with, which were implementing DevSecOps or shifting security left, were focusing on automating the security activities and then running as early as possible. And that's not bad, that's part of it. But if you only focus on the technology, in this case, like automating the activities and running them earlier, and you forget about the people and the processes, then you are doomed to fail, right? So at the beginning, you will have the impression that it's working. You will have the impression that because you automated things, it's kind of flowing and working, but at some point it will stall and it will fail. And the reason for that is that we really need to change deeply the developer and the security team practices in order for them to adopt these new activities and perform them in a way that lead to a successful implementation of DevSecOps. So the second misconception is that I have talked with many people that thinks that shifting left just stops at the coding level. And that's plain wrong, right? So we have to move them to the very beginning of the development lifecycle. Actually, it's very important to define security requirement as soon as possible, even right in the first line of code, so that we can then define the requirements, the policies that we can later enforce and make sure that they are applied during the development of the lifecycle. So I think those are the two main misconceptions for implementing shifting security left. The first one is very important, right? It's a cultural change. It's not just a matter of the tooling and automating things. And for performing and being successful with this cultural change, what we need to do is motivate our teams. And in his book, Drive by Daniel Pink, he tells us that motivation is a combination of three different elements. The first one is being autonomy, which means being free to do your stuff, like being in control. Then mastery, which is about the process of learning something new, about the process of enjoying knowing more about a given subject and becoming better at something. And then we have purpose, which is basically know why you do what you are doing. So if you think about many of the things that you do in a daily basis, you don't even know why you are doing that. So in most cases, people tell us to do things to fix this bug or whatever, and we don't really know the motivation or the why that is behind those changes. So if we apply those concepts to the implementation of DevSecOps, we can see that if developer teams just receive a huge PDF report from the security teams that keeps the control, that runs the tool, and then just handle these PDF reports with 100 of issues to the developer teams, developers are not in control, and therefore they won't be autonomous. In the same way, talking about mastery, if the expertise remains in the security team, the security expertise, and there is no a knowledge transfer to the developers, then developers won't be motivated to undertake new activities, undertake new responsibilities if they are not taking anything out of that. And then purpose, right? So if they don't know why they have to take this ownership of some of the security activities, if they don't know why they need to fix a certain bug, or they don't know the impact of that bug or anything like that, then they are not going to be motivated to perform these deep changes. And now Tony is going to explain a little bit the differences between DevOps and DevSecOps.
Exactly. So Alvaro has told you what do we want to do to shift security left, but to know how to do it, we can get inspiration from what DevOps has done in the past to bring closer the developers to the testers and the operations people. And then we can compare how that helps us with DevSecOps or shifting security left. Basically, what these two approaches have in common are the problems they try to solve, which are two mainly. One is misalignment between the teams, and the other is antagonism. So misalignment basically means that the goals between the teams are not aligned. Every team has a different goal. And this can be seen, for instance, when QA people were measured by the amount of bugs they were finding, right? So they needed to find a lot of problems and push the code back to the developers so they fix it. And that meant they were doing their job properly. Similarly, operations people were measured by the stability of the system, how little it changed. But developers constantly want to change the system and bring instability because they want to fix their software or add new features, which of course causes instability and friction between these two teams. Security is similar. If developers are constantly creating new features, adding new software, new code, these are opportunities to introduce a security issue that can escalate to a security incident, and then security people get angry because that happened and they couldn't control that. So you can see that the problems that are intended to be solved with these approaches are similar, but there are things specific to shifting security left that didn't appear in these other traditional approaches. So next slide. Thank you. So what's specific for DevSecOps? There are some specific problems that it tries to solve. And the first is the criticality of the bugs. It's not the same a QA bug that makes your application running 1% slower, or that it shows it misses a comma in a text, compared to a security issue in your application that allows an attacker to compromise your server and then install ransomware in your whole organization, right? This means that security issues need to be fixed with more urgency. And this also means that developers usually need to work late, extra hours, or even over the weekend, which of course causes friction and people get angry. There's also the scarcity of security experts or security researchers, because there are a lot more developers than security experts, which means that if you're a developer and you want to make a release in 2 hours, and you have the doubt that your code might have a security issue, but you want an expert to verify, you may discover that this resource is shared with your whole organization because it's scarce. And then you get frustrated because you need their help, but they are not there to help you in a short time. There's also a third specific problem, which is the bad reputation that some security experts or hackers have, especially in open source environments. You as an open source maintainer don't look with the same eyes to someone who is contributing code to your code base or fixing bugs, someone who's helping you, compared to someone who is just hacking your stuff and pointing fingers at you and saying, you have this issue, you need to fix it, or you will get hacked. People usually assume that there's economic interest behind it in the form of bug bounties, or there's just the intention to boost their reputation by finding interesting things, or just they want to have fun because hacking and breaking into things is fun, right? With all of this, which I mean is that the divide between developers and security people is just at another different level compared to QA and operations. So let's try to learn something from how DevOps fixed those issues and apply them to security. The first lesson is, well, if goals are different, let's try to align them. And by doing that, we can just change some words in how teams are measured or what their goals are. And you can see that things get easier. For instance, instead of saying to QA people that they need to find a lot of bugs, change that to that they need to prevent those bugs. And that suddenly aligns with what developers want, which is 0 bugs in their application. And then they can start collaborating and working together to reach that goal. Similarly for operations, if they stop caring for stability, because what they actually want is application uptime, then developers just need to find a way to deploy their code and make their changes without bringing the application down. If you achieve that, then again, operations and developers can collaborate to reach that goal. Similarly, for security, find a common goal. For instance, in the open source space, GitHub, specifically the GitHub Security Lab, is providing or giving out bounties to hackers, not for finding security issues and giving developers more work because they will need to fix those, but rather for writing pieces of code that automates the finding of those bugs, of those security problems. In that way, developers can automate the process of finding those issues and find those themselves, which takes work away from them. That's the first lesson. And second lesson is, as Alvaro told you, give developers autonomy and mastery. If developers can do those tasks themselves by having tools, for instance, tools that check their code for QA problems, for quality problems, or infrastructure as code tools that allow them to deploy their code automatically, suddenly they don't need to wait for anyone. They can do those tasks by themselves. And also they gain mastery, because to use those tools, they need to understand them and to understand what the tools are saying and what the problems are to fix them. This doesn't mean that the QA or operations teams are now useless. On the contrary, they are experts that are there and can be consulted, so that if developers have doubts or the tools need improvement or something needs fixing, they are there. But most of the time, developers are autonomous and have mastery. Same for security. As you will see next, security can be automated and can be used to empower developers in that way. Back to you, Alvaro.
Thanks, Tony. So as Tony said, one of the main levers for DevOps adoption was introduction of infrastructure as code. So all of a sudden, developers were able to set up their own infrastructure without having to open tickets on some ops system, provision them with some pieces of hardware, etc. They were able to do that using code. So they were able to read it, understand it, contribute to it, send a PR, and modify things without having to wait and be blocked by ops in this case. So if you think about testing, and as Tony mentioned, things were very similar. So in the pre-agile days, everyone or the developers were not responsible for the quality of their code. So basically they were writing code without having to care about the bugs. And then there was this other different team, QA, which were going to find the bugs for them and then report them those bugs through some different tooling or reports or whatever. So if you think about that today in 2021, it doesn't even make any sense, right? So every or most of the developers have adopted some sort of testing methodology, TDD, BDD, or whatever you want, but they took ownership of not introducing bug in their own code because it's their own code. They don't want to produce, silly code. So if that changed for testing, why is not the case for security in most of the organizations? So most of them, or many of them, have changed a little bit or are in the process of changing, but I would say that most of them are still operating in this disconnected way where we have security operating as a toll gate at some point in the development life cycle, while developers are not caring about security and just getting some information back from the developers teams at those toll gates. So we can fix that using security as code. And the best definition that I found of security as code is that is the methodology of codifying security and policy decisions and then socializing them with other teams. So there is a lot in this definition, right? So first of all, we have the security experts, which are normally the security engineers within your organization, which are codifying security and policy decisions. So codifying means that they're writing code to enforce or to express those security and policy decisions. They are not writing some Word documents in some place that developers need to be aware. They are doing that in code that developers are going to be able to read, understand, and then contribute. And that's part of the socializing of these practices and decisions. It's not about just handling them to the developers and you need to apply or comply with these policies. It's about socializing them. It's like all of a sudden, security is the responsibility of everyone in the company, and that means that it's a common goal and that they all have to look for achieving that goal, and developers can contribute and understand those security policies. And if they are not, they don't agree with some of them, they can contribute maybe fixes to make them more accurate or more to fit better their own technology stack. So we have to provide developers with policies about what they have to do, but also we need to provide them with the tooling about or how they can enforce those policies. And then we have to do that in their own tools, in your own tools. So that means that you have to be able to run those security tests as some sort of self-assessment or self-service within your IDEs and your build pipelines. So you can think that about like using more guardrails and fewer gates. So maybe we still need some like security toll gates at some very specific points in some specific projects, but for the most projects or most part of the life cycle, what we want to do is operate in the guardrail mode, which means that, well, if you think when you're driving, if you can drive at the speed that is allowed, but if you get very close to the reef, then there is going to be a guardrail which you are going to hit, and then it's gonna slow you down a little bit while you go back to the main lane. So that's the concept behind these guardrails. It's basically integrating security as code in the pipeline. So every time that you commit a new PR, you will get some feedback from the security policies, and then if there is maybe probably no bugs at all, but if you get one bug, it's not going to stop you. It's going to give you feedback and actionable feedback about how to fix it, and then you can continue driving at your DevOps speed. So what can be covered with security as code? Well, first of all, security policies. So that is like security policies that auditors and managers can now translate into code that basically developers can, as I said, understand, contribute, and even change. And then we have security testing. So security testing is normally when you are writing a non-functional security test for things like authentication or authorization. Well, you will write some unit tests for that, but not just that. When you get a vulnerability reported either by an internal security team or maybe a bug hunter or a security researcher, you will fix that bug. And then normally you will write a unit test to verify that that very specific instance of the bug in that particular piece of code does not get reintroduced later in the future in that particular file, right? But if you think about what NASA did, that sounds like more useful, right? Because they didn't wrote a unit test for that particular test, that particular file. They wrote a query that was making sure that that particular pattern was not going to manifest again. And with doing that, they were able to not just catch that particular bug, but also 30 other bugs. So if you codify your security testing with CodeQL or similar tooling test, but as code, then you will be able to apply it to the whole code base and even share it with other teams and even with the community, and then contribute to not reintroducing and just end with a whole category of vulnerabilities. Then we have vulnerability scanning, which is what Tony is going to show later in a demo. And here is where security teams and developers kind of unite like a common playground where the knowledge transfer happens, right? We have the security engineers that have the security expertise, and they are going to dump it in security queries that the developers will read and understand. It's not going to be some sort of PDF explaining what cross-site scripting is, but rather some code explaining what or how a cross-site scripting manifests so that they can understand it and better collaborate on that. So there are many benefits to security as code. Just to mention some of them, and I think I have mentioned some of them already, but just to reinforce them, we have developers and security finally speaking the same language. And it's not the same language, it's that the security teams also have to adopt developer practices such as version control, and then developers have to understand some security concepts like they are going to receive and they are going to learn and they are going to become better at, and then they are going to master, as we said before. Then because those policies are expressed in code, we can better audit them and review them. And then also we can automatically enforce them or apply them during the build pipeline or through self-assessments. So with that, I think now we are going to introduce finally what CodeQL is. And well, you can think about CodeQL as some declarative query language. So in some sort, it's very similar to SQL, but it will treat your code as data, and it will allow you to query your own code. So it will basically extract information about your code when you are building it, either through the integration with Maven or Gradle, for example. And then it will extract things like the abstract syntax tree of the code, the control flow graph, some semantics of the code. And then it will allow you to ask questions to the code, like just write queries and query that database. So it's not just about security, right? You can use CodeQL for whatever purpose you want. You can use CodeQL to find non-security bugs. Like if you found a bug in maybe some concurrency bug in some part of the code, maybe instead of just fixing that bug, you want to take that knowledge and dump it into a CodeQL query that you can then run on the whole application or even in other applications and find other instances of that bug, right? So with that, I'm gonna jump into VS Code, which is the official extension to write CodeQL queries. It's not the only one. For example, I wrote one myself for Vim because I'm a Vim user. So you can write one for your favorite ID. So with that, let me explain a little bit about the semantics or the main statements of a CodeQL query. So first of all, we have an import which will import the main libraries that you're going to use in the query. In this case, we are going to import the Java libraries, which will give us things like the method element here that we are going to use to find some interesting methods in a sample application. So then we have the from statement that is very similar to SQL. It will define what tables of this database you want to query. And then we will have normally a where statement where we will define some constraints for that selection. And then we will select elements to show as the result of the query. So with that, if I run this query on simple sample application that we use for this demo, it will show us that there are almost 19,000 methods defined in the code, but also in the libraries used by the code, by the application. Now, if we want to make something like more useful, maybe we want to find some specific methods. Like, for example, if you are writing an MVC application, you want to find all the controller methods. So you can do that by checking, like, for example, that an annotation exists, which, okay, I'm going to simplify this, but let's say that a controller method is that method. If we get the type of the annotation and then the name of that type, that would be a request mapping. I know that I'm not considering things like get mapping or put mapping or post mapping, and I'm also not checking if the enclosing class is annotated with controller or a REST controller, but just bear with me for this example. So we now have selected all the annotations whose type is a request mapping. Now, if we want to make sure that we select the methods that are annotated with this particular annotation, we want to say that that annotation is one of the method annotations. So with that, if we run this this query, it will narrow down the results to just a few of them, right? So probably like 4 or 5 of them, even I think a little less in this example. And as you can see, we have 3 controller methods. Now, if you think about using that in a reusable way, well, it's probably not the best way to put the constraint straight into the workflows. What we are going to do is we are going to take them from here, and we are going to write a predicate, which we can call something like is controller method, maybe. And it will verify that a given method is a controller method. And now in the where clause, what we can do is basically say, okay, is select all the methods, which are or which satisfy this predicate, this logical predicate. Now, if we run this, we will get the same results, basically because I haven't changed the logic of the query. We have the very same results. Now, if we want to make it even more reusable, one thing that is very interesting from CodeQL is that even though it's a declarative language, and this is not very normal or common in declarative language, we can use, it's also object-oriented. So we can benefit from things like inheritance, encapsulation, and so on. So we can say or define a class that is called controller method, and that extends from the method type, right? Now we need to define what we call the characteristic predicate, which you can think about as the constructor of this class. And then for this one, what we are going to say is exactly what we said before. We want those methods to be those ones. Let me delete this. And then we want them to be those ones that satisfy this predicate or this condition. And because this is a member predicate, we have to use this to refer to the class itself. Now we don't even need to apply a where constraint anymore. We can just basically say from the controller method, just select all of them. And then we will again get the same results because again, we haven't changed the logic of the application. So if we want to do something a little bit more security related, maybe what we can do is we can take this class and define another one, which we can say, like, for example, well, open controller method, we can call it. And we are going to see if we are going to extend the controller method. So basically, we are saying that an open controller method is a controller method, but in addition to have this request mapping, we are enforcing that it does not have something like, I don't know, maybe the pre-authorized annotation. Or we can check for secured, or just bear with me in this simple example. Now, again, we can do the same and query for all the open controller methods. And in this case, these results should change because if I recall correctly, the delete user is an authenticated method. So with this open controller method, what we are doing is basically querying or looking for all the methods that does not require authentication. And just to take it another step further, we can define, for example, the secured one. And then basically, well, I think the easiest way is basically saying that not this is an instance of open controller method. And again, if we run this, we should get the other one, right? The delete users, which was the only one that was secure in the sense that it was required some authentication. So by the way, just realize that I didn't click on any of the results, but if you click on the results, it will take you to the result itself in your code. So in this case, the delete user method. And with that, I'm going to handle it over to Tony, which is going to show you a little more complex example. So I'm going to stop sharing.
Thank you. I'm going to share my screen. And let's tell a little story here. So on the left, we have this demo example that Alvaro has been queried the code of. And as you can see, it's a simple application. It's used for managing users, and it just displays the user and the hash of the password of the users registered to it. Don't mind the security issue of the hash being displayed here. But if I wanted to register myself, I would just fill this form, and you can see that then I'm in the database. Now let's assume that we have a bug bounty program, and a bug bounty hunter decides to try some things in our application. One of the first things hackers like to do is to introduce special characters in our forms, so they can try to do just that with a double quote, and then boom, the application breaks. Right, so now they know that the special character did something, but what's happening? What's the issue here? Well, with a little of information gathering, they find out that the application is running using the Spring framework. And if you are familiar with Spring, you may know the Spring expression language, which is an expression language that allows you to graph some objects or even modify them using short expressions. Now, the issue with this is that if untrusted input, so something provided by the user or a potential attacker, reaches an expression and is able to modify it, then they can run arbitrary code in your application, which is bad, because with that, they can take control over your application server. So what they will try to do is exploit this vulnerability if it is there. And for that, they will use this payload. So they are working on the assumption that their input is reaching something like this, right? In which username is the information they provide. So if they insert this where the username is, you can see that they are just adding things at the beginning and the end of the expression to just not break it. But the important part, the malicious piece of code, is this, which is basically instantiating the runtime to execute a command in the operating system. In this case, it's just the creation of a file in the temp directory, but it could be something more malicious. So let's try to use that payload in the application and see what happens. For the record, let's just check that the file doesn't exist and it isn't there. But then if we click register, the application breaks anyway, the error appears anyway, but you can see that the file is there. So let's see what happened there. Basically, the user input came as a post request in this form, in the username field, and it entered our application. Now, in the CodeQL world, this is what we call a source. The information entering your application and provided by an untrusted source, it's called a source. Then this payload enters the application in a user controller, probably, or something like that. It gets encapsulated in an object, which we will call user form, and that object is tainted. It contains untrusted data. That object will travel through the application, entering and exiting methods, affecting other objects, maybe its contents being concatenated to a string. And finally, it will reach a method that is dangerous, that if it receives dangerous or untrusted input, bad things happen. In this case, it's the parse expression method, which parses and evaluates an Spring expression language expression. This, in CodeQL world, is called sink. So if a source reaches a sink, we have a problem. And to identify code patterns that model this path of data flowing through your application, we use taint tracking for finding those. So what we want to do now is writing a CodeQL query that will allow us to model this taint tracking pattern and find the vulnerability that this bug bounty hunter found previously and hopefully reported to us, and see if there are more like it. So let's use what Alvaro shown us to write this query. we will first begin modeling the sync, that parse expression method that we mentioned. If you know the framework, the parse expression method belongs to a certain object, which is called the expression parser, and it's an interface. So let's begin creating a CodeQL class for this interface, and its characteristic predicate, we'll just try to find it by qualified name, in which we will use the package of this interface, which is the following one. And its name is, of course, expression parser. Now we can try to quick evaluate this, which is a feature of this CodeQL Visual Studio Code extension, which allow us to run pieces of the CodeQL query, but not the full query. And you can see that the definition of the expression parser appears here. So this piece of code works. Now, we don't want the interface itself, but we want the method that is acting as a sync in this specific path. So let's try to find a call to that method. And in CodeQL world, a method call is called method access. So let's create that, and let's define its characteristic predicate. Now, what we want is for this method access to call a specific method, the one we are interested in. So let's use this exists formula that allow us to introduce something like a local variable. In this case, it's this method. And we will say that the method this method access is calling is that same M. And then we can start restricting this M to find the one we are interested in. So of course, we want this method to be declared in the type we defined above, the expression parser. And since it's an interface, let's use a trick of CodeQL, which allow us to find the supertype of this type. Now, we don't know how many types are in the hierarchy between the type we are interested in, the actual implementation of the expression parser, and the interface itself. So let's use recursion, which is this symbol here, and we'll traverse upwards the whole hierarchy of objects until it finds the interface. And then let's say that the expression parser we defined above needs to be there in that hierarchy. Now, this method access is defined as a call to any method in this interface in expression parser, but we don't want any method. We want specifically the parse expression one. So let's restrict also by name. Now we have this class that hopefully will find any call in our code that calls to this method we're interested in. And we see there's one in here. And if we travel there, we see that this is happening in the user controller class. So we are on a good track. Now we have our sync, we will need our source. But luckily for us, CodeQL already models a lot of the Spring libraries and provides a CodeQL library that already provides us Spring-specific inputs. So we won't need to model the source. You will see that in a moment. But what we need to do is create a configuration class that allow us to evaluate the taint tracking thing we mentioned earlier. So the thing that will know how to connect the source and the sync. Let's just call that SPL injection conf. And that needs to extend an object from the taint tracking library, which is the taint tracking configuration. And I need to import that same library for it to work. Okay, now that it's imported, let's create the characteristic predicate. In this case, for this kind of configuration, the characteristic predicate is just a string. It can be anything as long as it's unique. So let's just call that with the name of the class. And the important parts of the taint tracking configuration are two predicates. One is called isSource and receives a data flow node. And the other one is called isSync, which also receives a data flow node. Now here we define how which are the sources and the sinks, as we explained in this taint tracking config. As I mentioned, CodeQL already provides us with libraries for finding Spring inputs. So let's import that library, which is called flow sources. And the one we're interested in is remote flow sources. So this means that the source is restricted to be any kind of input that comes from a remote source, or in other words, that is untrusted. And now to define the sink, we need to use the expression parser, parse expression method access that we defined up here. But we don't actually want the method. The sink actually is the first argument of this function, which is the expression itself. And it's what we want to be tainted so that the vulnerability can reproduce. So let's introduce the parse expression parser method access that we define here, and let's get its first argument. Now here I'm using the any formula. This is similar to exists, only it allows us to just write it in one line. Now that we have the argument, we need to say that this is the sink. But since the sink is a data flow node object, let's just convert it to an expression, which is what an argument is in CodeQL. So let's quick evaluate this to make sure this is working. Yes, let's save the query. And we should see that the sink, as we mentioned, is the first argument of the method. So that works. Let's see also which sources are identified by this remote flow source object that comes predefined with CodeQL. And we can see that this object, source found three objects. One in the register method in the user form object, one is in the list users method, and one in the delete user method. You will recognize these methods from the ones Alvaro shown you in his demo. Okay, we have the taint tracking configuration. So the only thing that's left is selecting the important bits for the query to work. And I just copy pasted some boilerplate here. But what this is basically doing is saying that this configuration we are selecting here has a flow path from the source to the sink. That's it. And then the select query is just displaying prettily these results, but in a way that it shows the path from one to another. But for that path to work, we need to import an additional library, which is the path graph library. This is just for visualization. And another thing we need to do is define a bit of metadata, which is saying that this query is a kind of path problem. Now everything is in place. Let's run the query, and hopefully something will show here. And we have one result. There's one path, actually three paths between the source and the sink. We can review them quickly. The first one starts at register, which is consistent with what we saw in what the bug bounty hunter did. The user form, which contains tainted data, flows to, or is the method validate is called on it. So we navigate to that method, and we see that the get username method of the user form class is called and is passed to isFieldValid, which is another method down here that the query brings us to. And that method receives a field argument and passes it to the expression. So now here we can see that the username is concatenated and safely to an Spring expression language expression, and the vulnerability reproduces. So we found the issue. We could just add some sanitization here, escape some special characters, or restrict what the user can enter here, and be done with it. But we've seen that CodeQL reported two more paths. So let's look at them. The second path begins at the same point. It goes to validate, but then it's the get password method that gets sent to the isFieldValid argument, which means that the password input field here is also vulnerable to this vulnerability. And this wasn't known to us previously. No one reported it to us, but with this query, we saw it. You can guess what the third path. It starts in the same place, but then it's get repeated password, which is sent here, which we already know is vulnerable. So this field is also vulnerable. Okay, there are no more paths. So we could fix it at the sink, for instance, which is the common point between these three vulnerabilities, or at the input, or wherever we decide. We could just decide to not use SPL expressions anymore. But the thing is that with these 36 lines of code, we have gained three things. One, we found the vulnerability that was reported to us in the code, so we can quickly fix that. Two, we found two more variants of it, which we didn't previously know. And if we didn't fix them and we just fixed the first one, our application will remain vulnerable after the fix. And then some malicious hacker could do some damage when we believe we are protected. And the third benefit is that this is code, this is a query. This can be run in all your pipelines, in all your builds, in a way that if this gets fixed, but then a refactor comes and the vulnerability gets reintroduced because someone deleted the sanitization or something, this query will tell you, and you will know before the next release that the vulnerability reappeared, and you can fix it quickly early in the development stage. So that should be the demo. Going back to you, Alvaro, and thank you, everyone.
Thank you, Tony. Let me share my screen again. Okay, so yeah, as Tony showed, well, we can use CodeQL in our VS Code Studio or in our Vim, like I said before, or in the command line, because in the end it's a command line utility, or we can integrate that, as we explained, the basics of security as code is to integrate them into our build pipeline. And because it's a command line utility, you can integrate them with any of the pipelines like Jenkins or GitHub Actions or whatever tooling you are using. So in the case that you're using GitHub, you can use CodeQL for open source and public repos, for example, just by going to the security tab, clicking on the security tab and then enabling code scanning. And by doing that, it will create a GitHub action workflow, which will basically help you define when you want to run a CodeQL scan. Like, for example, every time that you submit a PR, you can check it for security vulnerabilities. So another thing that I wanted to mention is that CodeQL is community powered. And that means that even though the SEML, which was the name of the company before the GitHub acquisition, or GitHub engineers have worked on many CodeQL queries, many community members have contributed many queries to the main repo of the CodeQL. That, by the way, is open source. You can go to github.com/GitHub/CodeQL, and you will see that all the queries are open source and freely available. So just to mention some of the support that we have for the Spring, even though this is not comprehensive support, it's just something that I put together from the top of my head. We have sources obtained, as Tony explained, for things like Spring Web or Spring MVC, Spring REST. We have a specific Spring sinks. Like, for example, if, well, it's not the same having, well, it's the same category, like SQL injection, for example, but the way it manifests in a Spring JDBC is something that is a sink that is specific to Spring. So we have many of them already modeled. And the same thing goes with specific Spring categories. Those are vulnerability categories that are specific to Spring, like, for example, just to mention a couple of them, the Spring EL injection that Tony covered, or the Spring view manipulation. Now, I said it's community driven or community powered repo. And that means that we are receiving contributions from the whole community. So if you have something that is very specific to your technology stack, to your company, the way you apply or enforce authentication or authorization, well, that's something that belongs to you. But if you are modeling a new Spring module that was not covered, or if you are maybe modeling a vulnerability that was reported to you, like Tony just did, then you can actually share that. And actually, well, you can contribute them to the GitHub Security Lab. That, by the way, well, just to you can visit the securitylab.github.com to learn more about our mission. But just to mention some of the activities that we do, we try to find bugs in high-profile open source libraries and applications, like those open source components that most of us as developers use. We are reporting hundreds of CVEs per year. We also try to foster the collaboration between developers and security teams by aligning goals, just what we explained during this session. And we also try to empower other developers and security teams to do what we do, to find bugs by sharing our methodologies, articles, blog posts, advisories, even the tooling, like, for example, most of the CodeQL queries that we write. Last but not least, we also maintain and curate database of advisories, security advisories for open source components and libraries across different languages and ecosystems. So if you, as I said, I was saying, if you write a query that you think the rest of the community can contribute from, you can share them with us, and you can actually earn some money in the process. So last year we gave more than $100,000 in bounties just to people that were contributing queries to the community, really. So the CodeQL engineers like Tony will review them, will make sure that they are efficient, that they perform in a good way, and that they are complete, and then they will put them into the main repo. So with that, that's all we have for you. I hope that you enjoyed it. If you have any questions, we will have now a Q&A session in a different Zoom, or in a different room. And if you want to reach out later to us, you can use our Twitter handles, _A_Torralba or GH Security Lab. So with that, thank you very much, and stay secure.
Thank you, everyone.
Wow, thank you so much, Alvaro and Tony. That was absolutely really, really fun demos. And definitely, if any of you who have done regulated industries or whatever, you know that security automation is really, really a big challenge. So definitely encourage all of you to follow up if the environment, the CodeQL environment, looks really useful for your purposes. I'll remind you that Alvaro and Tony are moving to the Slack channel, which you can find in the Slack environment as -as-code-a-DevSecOps, approach. But by far the easiest way to get there is to find the session page on and click on the join the discussion button there. And with that, thank you very much. And we hope to see you in some future sessions here in the Cloud Native Platforms track.